Hi, good morning. So this is EDEXCEL Further Maths Chapter 1 Complex Numbers, and this is section 1.6. It's on page 20 of the textbook, and we're talking about nth root of a complex number. This is one of the most useful thing about complex numbers, that you can find any root like square root, cube root, fifth root, 10th root of any complex number, and we take help of De Moivre's theorem in this. Okay, so I'm going to go over a couple of examples and do some questions together. Okay guys, this first question talks about z cube equals 1, where z is a complex number. That means if you go, you're going to find z is 1's cube root. And guys, in the real number system, we thought cube root of 1 is 1 because any power of 1 is 1. But in the complex number system, we'll get 3 different answers. They're very popularly known as cube roots of unity. Okay, so we will start from there. All right, the first question I'm attempting is where it says z cube minus I equals 0. So I will write down in the equation z cube equals to I. Step 1, people, we write this complex number, which is 0 plus I, into mod arg form. Okay, so what you need to do is you have to find the modulus, and you have to find its amplitude as argument as well. Sorry. So guys, modulus is, this is where the complex number is, because 0 on the real axis and this 1 on the imaginary axis. Okay, so modulus of z is equal to 1, and the argument of z is equal to, from the real axis in the anticlockwise direction, this is pi by 2. So guys, z is 1 cos pi by 2 plus iota sine pi by 2. Okay, so what we need to do now after that is, guys, we need to be writing this into the complex form. So guys, we write this equation. This will be z cube is equal to cos pi by 2 plus iota sine pi by 2. Okay, then basic algebra. So z is equal to cos pi by 2, shouldn't have put this bracket, plus iota sine pi by 2 to the power 1/3. Really important, guys. Now we're going to use De Moivre's theorem to bring the equation down, but then we're going to understand that cos and the sine functions are the periodic functions. They have the periodicity of 2 pi. They get repeated after 2 pi, so we're going to be adding 2 pi's into it. So this will be cos pi by 2 plus 2k pi, okay, plus iota sine pi by 2 plus 2k pi, and all the power 1/3. Now guys, now we use De Moivre's theorem. What happens? The power gets multiplied to the angles there, isn't it? So this becomes cos, this is pi by 2, so pi plus 4k pi over 6, because there will be 2 at the bottom, and plus iota sine, same thing, pi plus 4k pi over 6. What do you do after that, guys? You put k equals 0, k equals 1, and I always say k equals minus 1 as well. Okay, when k equals, what happens, guys? This is 0, so this becomes z equals cos pi by 6 plus iota sine pi by 6. That's my first answer. So when k equals 1, what do I get, guys? Cos 5 pi by 6 plus iota sine 5 pi by 6. When k equals minus 1, that will give me what, guys? When k equals minus 1, I put minus 1 there, so pi minus 4 pi, it says minus pi by 2, so cos minus pi by 2 plus iota sine minus pi by 2. So these 3 are the cube roots of this complex number. So we were able to find the cube root of complex number I. These 3 are. So guys, very important. Why did I do 0, 1 and minus 1 is because I want to keep my principal argument between minus pi and pi as decided earlier. Okay, so we do more questions now. So right, the sixth question of the same exercise 1F is this now. Let's go over it. Step 1, it says find the modulus and argument. So guys, I'm expecting you to know this, but let's do this together. So modulus of z is equal to minus 2 squared plus minus 2 root 3 squared. That gives you 4 plus 4, 12 square root, and this is 4. Good, neat argument, neat modulus. So how do you find the argument? You always plot the number first, so minus 2 over here and 2 root 3 over here. Okay, so this is the complex number, that's where the z is, and looking for this angle as the argument. So let's find this theta first. So theta is equal to tan inverse of minus 2 root 3 over minus 2. So that gives you tan inverse of root 3 is pi over 3. Okay, so your argument of z is not this theta. This will be negative pi minus pi over 3, which is negative 2 pi by 3. Right, so z can be written as 4, then I say cis negative 2 pi by 3. Okay. Now if you want to solve this equation, that equation gives you z4, take this to the other side, is equal to minus 2 root 3i, which is exactly the same complex number which we use the model forms. We can write this z4 equals to 4 cis minus 2 pi by 3. Okay, so guys, now we start doing our algebra from here. So z is equal to 4 to the power 1 4, and then cis minus 2 pi over 3 to the power 1 4. Okay, then we solve this. This is what? 2 squares, this will be square root 2, and that becomes, guys, before we use the removes, what do we need to do? We have to add 2k pi. That becomes cis minus 2 pi by 3 plus 2k pi 1/4. Simplify this if you want to. That gives you cis minus 2 pi plus 6k pi over 3, then 1/4. So guys, you're using removes now. What happens? This will be a square root of 2 cis minus 2 pi plus 6k pi over 12. Okay, so now we do what? Same old business. K equals 0, k equals 1, k equals minus 1, and we want to do one more because we're expecting 4 answers there, right? Depending. Okay guys, when k equals 0, what does that give you? Z1 is equal to root 2 k is 0, so this is minus pi over 6. Yeah, root 2 cis minus pi over 6. It's in the range. Yes, it is. K equals 1, z2 equals to root 2 cis k equals 1, so 6 pi minus 4 pi over 12 pi over 3. That's also in the range. Z minus 1 is equal to minus 2 minus 6 minus 8 pi over 3, so minus 2 pi 8 pi over 12, so minus 2 pi over 3, so root 2 minus 2 pi over 3, and we're going to do k equals 2. Let's try k equals 2 there, guys. What do you get? 12. K equals 2 gives you what? 12 pi, and so 10 pi over 12, so z4 is equal to 10 pi over 12 root 2 cis 5 pi over 6. So they are in the roots, guys. They are in the range. They're all between minus pi and pi. So they should be the answers. We can check the work, check the answers in the book to see if the answers match with what we have done. Thank you. Very important concept in complex number planes is the roots of unity. Obviously, it's not important to find out what they are. Obviously, it is important as well, but more important is their use in geometrical problems. Alright guys, we're going to try and make a relationship between the cube roots of unity. Then I will try to find the fourth root as well. By the way, unity is I'm referring to is number 1 in complex plane, which is 1 plus 0i. Okay, so let us try to find out what are the 3 cube roots of unity, what are the 4 fourth roots of unity, and so on and so forth. I'm trying to see if I can explain the relationship between them as well. Right guys, let's see. Z cube is equal to 1. This is a cubic equation in complex plane, should have 3 roots. I mean, in cubic equation should have 3 roots. Okay, so let's check. What do we do? Z cube is equal to 1 plus 0i. Then we write this in the cis form, the mod arc form. Okay, so this is Z cube is equal to argument is modulus is 1, argument is 0, so this is 1 cis 0. So Z is equal to 1 cis 0 to the power 1/3. But then we know, because of the periodic nature of sine and cos functions, we do Z is equal to 1 to the power 1/3. I'm splitting this over here, and before I do that, I do cis 0 plus 2k pi to the power 1/3. So I got Z is equal to 1. So cis 2k pi over third. Okay guys, so now we do what? We find the Z1, Z2 and Z3. That comes out as what? When k equals 0, this is cis 0. Okay, when k equals 1, that gives you cis 2 pi over 3, because modulus is 1. When k equals 2, that will make it more than pi, so which I do not like to take as principal argument, so I'll take k equals -1, so I get cis minus 2 pi over 3. Okay, so write all these 3 in polar form as well. So what does that give you? R, which is 1, e to the power 0 pi over 0 pi I, okay, which is 1 anyway. So this is e to the power 2 pi over 3i, and this is e to the power minus 2 pi over 3i. Right, so if you want to write these numbers into algebraic x plus iy form, so this is 1, that will be cos 2 pi over 3 is a negative, this is, so it will be minus half, then sine is positive, plus root 3 over 2i, and this is minus half minus root 3 over 2i. Okay, so these are the 3 cube roots of unity, and we call them as w1, omega, and omega square. Right, this is just the notation, people. Right, the 4th root, I'll do the calculations, leave that to you. Please finish the calculation, we work out the answers. Okay, so following on the same process like we did over there, guys, we get the 4 answers, which are 1 cis pi by 2, cis pi, and cis minus pi by 2. Really important is this one over there, rather this one I would say, and this one over there as well. What do you see in the connection, people? You're trying to find the cube roots of unity. The primitive cube root of unity, obviously after 1, is 2 pi over 3. And the primitive cube root of unity, 4th root of unity after 1 is 2 pi over 4. And there's a connection which I followed. I'm sure you would look at it as well. If I ask you to find the 5th root of unity, so it will be 1, and then it will be cis 2 pi over 5. That's your primitive root of unity. Then obviously next ones will be, which you can see here, 1 omega and omega square. This will be 1 omega square, omega cube, and then next one will be omega square, omega cube, omega to the power 4 over there, guys, in the 5th root of unity. So the important part is I would like you to make you understand the primitive root of unity. Any root of unity is says 2 pi over that number. If it's 4th root, it's over 4. If it's the cube root, it's over 3. And if it's 5th root, it's over 5. Lovely. Now, where do we use this cube root of unity? Oh, sorry, I keep saying cube. Nthroots of unity is in solving equations like this. Okay. And if you know one solution or the root of this equation, okay, then you can find all the other roots of the equation, roots of this equation. And how do we do that? You just times the z1, the first root, times, but let's say it's called it z1, okay, by all the nth roots of unity. Okay, so times this by this, all this will be the roots of that equation, zn equals p. That means nth root of a complex, where p is a complex number, by the way. Okay, this is a complex plane we're talking about. Okay, this is the bullet point given to you on page 25 of the book. It's really important to understand this equation. Okay, so what does that say? If you know one root of any equation, z to the power n equals s, and these are the nth root of unity, and it could be 5, these will be 5 of them, 5th roots of unity, then all the roots of this equation would be the first root times by all these. Right? It's used quite a lot in geometrical problems. Another thing which you need to know, people, is this, that this is a very important concept. The nth roots of any complex number lie in the vertices of a regular polygon at centrist origin. Okay, so what we're going to do, guys, we're going to be using this to solve some geometrical problems. I'll do only one. This is exercise 1G. I'm going to write the question there. And let's do part C of this. I'm not looking, just at random part C. Okay, you can read, right? You can pause the video if you want, read, or you got the book, you can read from there. Okay, we're doing one part. All right, the question is, find coordinates of remaining vertices of a regular pentagon with center at origin. Okay, and if one of the vertex is -1 root 3, obviously we're talking an Argand diagram, but we in these questions, to make the geometry look easy, we're just transposing the Argand diagram into normal Cartesian plane. Okay, so if one vertex is given, we're going to find the other vertices, and you'll be surprised that this concept of cube root of unity and this equation and the concept of nth roots occurring vertices of regular polygon will help you find this. Alright, what I'm going to explain to you a couple of basics there. Okay, so this is the point, one vertex. Then we know that the nth root of any complex number, they do what? They occur as the vertices of a regular polygon. Right, so we're talking about pentagon. That means there will be 5 corners, and one of them is -1 root 3. Okay, that's for argument's sake. Obviously, guys, this is not accurate. So this is the first complex number which we have got. Okay, let's write that in the cis form. So its modulus is -1 squared plus root 3 squared square root. I'm pretty sure you can do this job properly. That's a 2. Okay, and its argument is, if I've measured this angle theta, because I always prefer drawing and then taking the argument. So this will be root 3 over 1. This angle is, this theta is equal to tan inverse of root 3, which is pi over 3, 60 degrees. So guys, the argument will be pi, this whole bit, minus pi over 3. It is 2 pi over 3. So in the polar form, guys, this complex number, the first vertex is 2 e to the power 2 pi over 3. Right, so if the equation was z to the power 5 equals some complex number, okay, whatever complex number, right, and you know the first root of that is equal to 2e to the pi over 3, Using the theorem which we learned on the top, guys, if you have to find the second other roots of this, I have to first look for fifth roots of unity, okay, because there will be 5 corners, and the concept I described you over there, guys, this thing, right, this thing. So primitive fifth root of unity would be omega. Here would be it would be, guys, cis 2 pi over 5, or if you want to write in polar form, this will be e to the power 2 pi over 5 I. Okay, so that's omega. Now we will be doing what? We're going to be finding the other roots by this one time, that's the first root, this one times omega will be second, omega square, and so on and so forth. We find out all the other 4 coordinates now. Right, so the other 4 roots of that equation would be z2 would be z1, which is 2 e to the power 2 pi over 3 times by omega e to the power 2 pi over 5 I. Okay, so let's see, simplify, let's see what we... Right, I kept missing this I is there, by the way, in z1. Okay, so this gives me 2 e to the power, powers get added, 2 pi over 3 and 2 pi over 5, that's 15, so 10 pi, which will be 3 6 pi, 16 pi over 5 I. So that's your second root. Okay, so similarly we're going to find this word 2 e to the power 2 pi over 3 I times e to the power 4 pi over 5 I. Isn't the square of that will be 4 pi over I, and so on, and we work out the answers remaining of these as well, guys. So I'll leave that to you, just work it out and mark check answer with mine. Okay, so that will help us figure this out properly. Right, so these are the answers. Have a look. So I got 2 e to the power 16 pi over 15i, 2 e to the power 22 pi over 15i, 28 pi over 15i, and really important, we got 34 over 15i over here, and which turns out to be 2 to the power 4 pi over 15. Guys, this is an important point for you to understand when you do it for the first time, because 30 pi over 15, okay, would actually complete the whole circle. So we take out the multiple of 2 pi from there, it's left over with 4 pi over 15. Right, so guys, these are the complex numbers which will be the roots, which will be the vertices of the other 5, which corners are the 5 corners of the pentagon. So let's write these in the x plus iy form to get the coordinates. Okay, so that shouldn't be very hard. Let's try this one. Okay, so we're going to be trying this one there. So 2 e to the power 16 pi over 15i. Let's write in x and y form. What does that give you, people? This is 2 cos 16 pi over 15i. Okay, and plus, so 16 by 15 plus iota sine 16 pi over 15. Okay, let's work it out what the coordinates are, please. So this does not give me an exact answer, so I'll leave it here then. 2 cos 16 pi over 15 is my x coordinate, and 2 sine 16 pi over 15 is my y coordinate on the Cartesian plane. Okay, so that's my second point. Similarly, you can find the third and the fourth and the fifth points coordinates. So this is how we start the basic use of cube roots of unity, and we finish the questions of the exercise. Let's see if there are any issues.